for the next yeah, right. So let us talk about the last unit, network. About the network analysis. Now the network synthesis. So what is we will do. Right. Okay. So we will discuss first. We will discuss what is the difference between network analysis and network synthesis. Let us slowly move into the content of the network synthesis. Right. So what is the main difference between the network analysis and network synthesis? Network analysis means we have the circuit, and for that circuit we need to calculate the response. See, if we have an electric circuit and if you provide some input excitation, that excitation may be a voltage or current, and we are going to calculate the response in the circuit. That response also again either voltage or current across the element or through the any element. The complete process is related to the network analysis. So I want to repeat once again. In network analysis, we have a circuit which containing a different passive elements. Further circuit, we are giving some input excitation. That input excitation may be a voltage or maybe a current. And later, we are going to calculate the response. That may be a voltage response or that may be a current response across some element within that circuit. That is called as a network analysis. We are analyzing the network by calculating the response for a given input excitation for a given combination of the passive elements. That's what we discussed in the network analysis, right? So simply in network analysis, we have the electric circuit. That's a combination of different passive elements. And we have some input excitation, either voltage or current. That information is available. And we need to calculate the response. That may be a voltage response or that may be a current response by using different techniques, right? So different techniques means like either KVL or KCL or mesh analysis or node analysis. By using these techniques, we are going to calculate the response. So that's what we discuss in the network analysis. Okay. Yeah, someone told that my voice is not audible. So once again, I want to repeat. Please let me if we have any issues again. Okay. So before moving to the network synthesis, okay. Before moving to the network synthesis, let's try to recap network analysis, what we are doing. In network analysis, we have an electric circuit which is combination of different passive elements like resistance, inductance, and capacitance. At the same time, we have an input excitation. That input excitation either a voltage source or current source. So this information is available. And using this information, we are going to calculate the response. Again, that response is either voltage response or current response. Okay. So this is what we are doing in network analysis. We are calculating that response in that given circuit for the given excitation by using different techniques like mesh analysis, node analysis, KVL, KCL, series parallel combination, etc., etc. Okay, that is what we are discussing in the network analysis. Like this. So some circuit is given. There is a combination of different passive elements, and input excitation is given, and we need to calculate the current flowing through the particular resistance or voltage across the particular resistance. Such type of problems we are dealing in the electric circuit 1 and also in the electric circuit 2 up to now. Okay. So in all the cases, we are calculating the response by using the different techniques like KVL, KCL, mesh analysis, and node analysis, and series parallel prediction, whatever it may be. Okay. At the same time, whatever may be the technique we are using, but the response is a constant. Response will be same. Response is a unique, right? See, unique solution. So in the network analysis, whatever may be the technique you are using, either series parallel connection reduction, or if you are using KVL, or if you are using KCL, or if you are using mesh analysis, or if you are using node analysis, or if you are using series parallel reduction, whatever may be the technique you are using, the response will be same. It will not change. That is a unique solution. You need to calculate the response. That is the solution. That is a unique solution. See, let us assume if this is a circuit and I want to calculate the current flowing through the 105 ohms. Suppose if I am getting the current flowing through the 105 ohms equal to 2 amperes by using mesh analysis, same 2 amperes will be flowing when we are using node analysis. Same 2 amperes we are getting when we are using the series parallel reduction. That means the solution will be unique, whatever may be the technique we are using. That is what about the network analysis. Hope you understand. Now, going to network synthesis. Now we are moving to network synthesis. So network synthesis means in the network synthesis, we have a function. We don't know the circuit, right? We don't know the circuit, but what we are doing in the network synthesis is we have a function for represent the circuit. I don't know the circuit. What are the elements inside the circuit? I don't know. Only what the information I have is some function related to a particular circuit I have. By using the network function, I want to calculate, I want to find the circuit elements. I want to find the circuit elements, right? So simply I'm telling that if the circuit elements are available, I'm going to calculate the response that what we are doing in the network analysis. But if the response or some function is available, some network function is available, that may be an impedance function or that may be an admittance function. So some function is available. By using that function, I am going to estimate the topology of the electric circuit. How the electric circuit looks like. How we connect the series parallel combination of the passive elements. How we design the circuit based on the network function. That's what we are doing in the network synthesis. Just reverse process. Right? In network analysis, we have the circuit and we are going to calculate the response. But where in the network synthesis, we have the network function that may be impedance function or admittance function in S domain. Admittance function or impedance function, some network function in S domain. By using that function, we are going to find the circuit. So we don't know the circuit initially. We have the function information. From that network function, we are going to estimate the circuit. That what we are doing in the network synthesis. That is the reverse process. Right? So there's a different techniques like Foster method, Carrier method, which are used to solve network synthesis problems or to design electric circuit based on the given network functions. Right? Whereas in the network analysis, whatever may be the technique we are using, the response will be unique. It will not change. But whereas in the network synthesis, we have only one network function, but for different approaches, we will get the different type of electric circuits. We will get the different type of electric circuits. That means, so may have a multiple solutions, may have a multiple solutions in the network synthesis. Whereas the network analysis is a unique solution, but in the network synthesis, it is a multiple solution. Hope you understand that small difference. Try to understand. Okay, I hope you understand. So once again, I want to repeat. Network analysis and network synthesis. The complete network theory you are doing with the network analysis and network synthesis. In electric circuits, up to now you are dealing with the network analysis only. In the network analysis, you have a circuit parameters, you have a circuit and you have an input excitation that may be a voltage or a current, and you are going to calculate the response by using the different techniques like KVL, KCL, series, parallel, some etc. And that solution, that response will be unique. It will not change with respect to the technique. Whether you use KVL, whether you use KCL, whatever may be, the current flowing through the particular resistance in the same circuit for the same excitation will be remain same. That is unique. But in the network synthesis, we don't have any circuit. We don't have any electric circuit. What information we have is, we have a network function. That may be an impedance function or that may be an admittance function in S domain. And based on that network function, you are going to design the electric circuit. Reverse process. You are going to design electric circuit. That is a reverse process. That what you will do in coming classes in the network synthesis. There are different techniques in the network synthesis as listed here, Foster and Carrier. So unlike network analysis, it is not a unique solution. There may be a multiple solutions for the multiple techniques, right? So what the prerequisites for the network synthesis? Network functions. Prerequisite for network synthesis, network functions. So now we will discuss about the prerequisites about the network functions. We will discuss now. Okay, so మన network synthesis మనం deal చేయాలనుకుంటే we must have some knowledge about the network functions. Now our first task is introduction about the various network functions, and later we'll move to the synthesis flow. Good, but most of the contents what we discuss will already covered in the two-port network and also in the Laplace transforms. But we will explore something else, right? See, let's assume this rectangular box will represent a network with different passive elements. This is a network. Let's assume this is a network which is the interconnection of the different passive elements, and this is the port or terminal. Port is nothing but a terminal. Man define cheyadam. Two-port network chaduvukunnappudu cheppanu. A port is a pair of terminal where we can inject the power, or from where we are drawing the power, or where we are inject the energy, or from where we are drawing the energy. That is called port. So this is the port for this network, and this is the single port, one port network. This is the one port network. That one port having the input voltage V and current is I, right? The pair of terminals which is connected to energy sources is called energy sources, called driving force of network, or called the driving point of the network. Ante నేను ఇక్కడ ఒక ఎలక్ట్రిక్ నెట్వర్క్ తీసుకున్నాను, and this electric network has a pair of terminals. It is called the port. Okay, if this port is connected to some voltage source or some current source, that voltage source or current source is called as a driving force. Okay na? So ఏ టెర్మినల్స్ కి అయితే ఆర్ ఏ పోర్ట్ కి మనము ఈ డ్రైవింగ్ ఫోర్స్ అంటే వోల్టేజ్ సోర్స్ కానీ కరెంట్ సోర్స్ కానీ కనెక్ట్ చేసుకుంటామో, ఆ టెర్మినల్స్ ని, ఆ పాయింట్స్ ని, ఆ పోర్ట్ ని డ్రైవింగ్ పాయింట్ ఆఫ్ ది నెట్వర్క్ అంటారు. అంటే మన యొక్క నెట్వర్క్ లో ఏ పేర్ ఆఫ్ టెర్మినల్స్ కి ఎనర్జీ సోర్స్ కనెక్ట్ చేస్తాము, ఎనర్జీ సోర్స్ ని డ్రైవింగ్ ఫోర్స్ అంటారు. డ్రైవింగ్ ఫోర్స్ ని కనెక్ట్ చేస్తాము. డ్రైవింగ్ ఫోర్స్ ఇస్ నథింగ్ బట్ ఎయిదర్ వోల్టేజ్ సోర్స్ ఆర్ కరెంట్ సోర్స్. అంటే మన ఎలక్ట్రిక్ నెట్ సర్క్యూట్ లో ఏ టెర్మినల్స్ మనము వీఆర్ కనెక్టింగ్ ద వోల్టేజ్ సోర్స్ ఆర్ కరెంట్ సోర్స్, those pair of terminals, that points are called as driving point. That point is called as driving point. So here in the single port network, and these terminals are, these points are called as the driving points of the network. Driving points of the network. Similarly, you can, that maybe this is a single port, that may be a two port or three port or multiple number of ports. That may be a two port, three port or multiple number of ports. Right? So if you consider this port a two port network, so this is the input port and this is the output port. Okay, so the port where we are connecting the separators, at the input port I am connecting some voltage source, then these pair of terminals or these points is called as the driving points. And if you connect the load across these two terminals, it is called as the load points. Otherwise, suppose if I connect the voltage source or current source at the second terminal, and I am connecting the load at the first terminal, then the second terminal will become a driving point. That means the terminal or pair or points of a network to which we are connecting the connecting the voltage source or current source, that is called as the driving forces. Those points or those pairs or those terminals are called as the driving point terminals or driving points of the network. So I hope you understand what mean by the driving point. What mean by the driving point? అంటే మనకున్న సర్క్యూట్స్ లో ఆ సర్క్యూట్ కి ఎన్ని నెంబర్ ఆఫ్ పోర్ట్స్ ఉండొచ్చు, ఎన్ని నెంబర్ ఆఫ్ పేర్ ఆఫ్ టెర్మినల్స్ ఉండొచ్చు. అది వన్ పేర్ కావచ్చు, వన్ పోర్ట్ కావచ్చు, టూ పోర్ట్స్ కావచ్చు, త్రీ పోర్ట్స్ కావచ్చు. ఏదైనా పోర్ట్ కు వీఆర్ గివింగ్ సమ్ ఎగ్జైటేషన్, వోల్టేజ్ కరెంట్ ఎగ్జైటేషన్ ఇస్తాం. సో ఏ టెర్మినల్ కి అయితే మనం ఎగ్జైటేషన్ ఇస్తుంటామో దట్ టెర్మినల్, దట్ పాయింట్స్ ఆర్ కాల్డ్ as the driving points. That excitation is called as the driving force. That's it. I hope you understand driving point. Now we will discuss about some transform network functions. So network functions are classified into two categories. One is transform function and it is called as a transfer function. Please try to understand the difference. Transform functions and transfer functions. Again, transform functions are again categorized into two types. One is transform impedance function, another is the transform admittance function. Transform impedance function and transform admittance function. Right? So these are the network functions. Generally, these network functions are used to find the electric circuit parameters in network synthesis. Okay. So these are the functions, transform functions and transfer functions. So transform functions again classified into two categories. One is the transform impedance function, and another is the transform admittance function. Right? Now we will discuss about the one by one. See, maybe you feel the names are somewhat new, but all the things you already discussed, you already learned in the two-port networks. See. So what is the transform impedance or admittance function? So generally it's called as a immittance. IMMITENCE, immittance. Immittance nothing but admittance and impedance. It's called immittance. So transform admittance or transform impedance, how we define, right? There is small correction in the third equation. That's not a Z of S, it's a Y of S. I will modify later. So transform impedance at a port. Try to understand. So electric circuit, they may have any number of ports, single port, two port, three port, or multiple number of ports. Okay. So transform impedance at any port, transform impedance at any port is the ratio of voltage transform and current transform for the network in the zero initial state. Right? So transform impedance is defined. Transform impedance at any port of the network. Either suppose if it is a single port at this port, if it is a multi-port, either here or here at any port. So transform impedance at any port is defined as the ratio between transform voltage and transform current with a zero initial condition. Why I am telling transform voltage, transform current is because generally current and voltage parameters are in the time domain. We are transformed into the S domain. So that S domain parameters we are going to use for calculating the network function. In the statement, I am not telling only ratio between voltage and current. It's the ratio between voltage transform and current transform. Voltage transform means the given time domain voltage is transformed into S domain. Given current excitation or given current in the time domain is transformed into current in the S domain. So after transforming the voltage and current parameters, now we are taking the ratio between transformed voltage and current at the particular port where we want to calculate the transform impedance. Right? So that is called transform impedance. So transform impedance is defined as Z of S equal to V by S divided by I by S. Try to understand the statement. A transform impedance at any port is the ratio of voltage transform V of S and current transform I of S with zero initial condition. Zero initial condition means definitely a network is a combination of the passive elements that may be a resistor or inductor or capacitor. If there is a resistor, nothing an issue. But if it is inductor and capacitor, there is a storage elements. So zero initial state means we are assuming that there is no initial current is flowing to the inductor, no initial voltage across the capacitor. That is the zero initial state. We assume that no initial current, no initial voltage across the energy storage elements like inductor and capacitor respectively. Right? So this is how we define the ZFS. Similarly, YFS, there is the reverse, reciprocal of the impedance. So YFS equal to IF. This is the YFS, not ZFS, there is the YFS. So YFS equal to the ratio between transform current to the transform voltage of a network at the with zero initial state. Right? So see, you have to observe one thing. Suppose if we have electric circuit, and if that electric circuit has a multiple number of ports, electric circuit has a multiple number of ports. At each port, I want to calculate the transform impedance. And if we going to calculate the transform impedance at any port in the electric circuit, then you have to take the ratio between transform voltage and transform current at that port only. Okay, na? So if you want to calculate the transform impedance you want to calculate the transform impedance, or if you want to going to calculate the transform admittance, so I want to correct these things. It is the transform impedance, it is the transform admittance. I will correct it later. It is not a ZFS, it is the YFS. Okay. Suppose if you want to calculate the transform impedance or transform admittance at any port on a given, in a given electric network, in a given electric circuit, then you are going to calculate the transform admittance or transform impedance by taking the ratio between the transformed voltage and current, where these two parameters you have to consider at the port only. అంటే సింపుల్ మీకు ఏం చెప్పాలనుకుంటానంటే, మన దగ్గర ఒక ఎలక్ట్రిక్ సర్క్యూట్ ఉందనుకోండమ్మా, ఆ సర్క్యూట్ కి మల్టిపుల్ నెంబర్ ఆఫ్ పోర్ట్స్ ఉండొచ్చు. అది సింగిల్ పోర్ట్ కావచ్చు, 2 పోర్ట్ కావచ్చు, 3 పోర్ట్ కావచ్చు, n నెంబర్ పోర్ట్స్ కావచ్చు. ఏ పోర్ట్ దగ్గర అయితే మీరు ట్రాన్స్ఫార్మ్ ఇంపెడెన్స్ క్యాలిక్యులేట్ చేయాలనుకుంటున్నారో, సో ఎలా క్యాలిక్యులేట్ చేస్తాము? బై టేకింగ్ ద రేషియో బిట్వీన్ ద VFS అండ్ IFS, ట్రాన్స్ఫార్మ్డ్ వోల్టేజ్ అండ్ ట్రాన్స్ఫార్మ్డ్ కరెంట్. ఇఫ్ ఇట్స్ అడ్మిటెన్స్, IFS by VFS, ట్రాన్స్ఫార్మ్డ్ కరెంట్ అండ్ ట్రాన్స్ఫార్మ్డ్ వోల్టేజ్, right? You have to choose the transformed voltage and transformed current at the same coil, same port where you want to go, where you going to calculate the impedance. ఏ పోర్ట్ దగ్గర ఇంపెడెన్స్ క్యాలిక్యులేట్ చేయాలనుకుంటున్నారో ఆ పోర్ట్ దగ్గర ఉన్న వోల్టేజ్ కరెంట్ మాత్రమే మీరు తీసుకోవాలి ఫర్ క్యాలిక్యులేటింగ్ ద ట్రాన్స్ఫార్మ్ ఇంపెడెన్స్ ఆఫ్ ఎనీ నెంబర్ ఆఫ్ పోర్ట్, any number of port network, right? So that's the note here. Voltage and current transforms which have considered to define the transform impedance or admittance are considered from the same port. Right? Now, so transform impedance and admittance are also called as transform impedance or transform admittance are also called as the driving point impedance or driving point admittance. Why it's called as a driving point impedance or driving point admittance? Because we are going to calculate the impedance or admittance at the pair of terminals. So pair of terminals ante generally we are giving the driving force, either voltage source or current source connect chestam. Kabatti driving force antam. So driving force ni ekkada connect chestam, danni driving points antam. So that impedance is called as a driving point impedance or admittance. Okay. So transform impedance or transform impedance is also called as a driving point impedance or driving point admittance, because we are going to calculate the admittance and impedance at the points, driving points. Why it's called as a driving points? At that point we are giving the excitation. That may be a voltage excitation or that may be a current excitation. అందుకని వాటి డ్రైవింగ్ పాయింట్స్ అంటాం. ఆ పాయింట్ దగ్గర మనం ఇంపెడెన్స్ క్యాలిక్యులేట్ చేస్తున్నాము, ఇంపెడెన్స్ క్యాలిక్యులేట్ చేస్తున్నాం కాబట్టి దట్ ఇస్ కాల్డ్ as a driving point impedance or driving point admittance అంటారు. So simply trying to remember transform impedance or driving point impedance, transform admittance, driving point admittance, all are same. Right? Now my question is, in front of you are able to see one screen. It containing the T network. Generally we are using for the last few classes. Now tell me, what is the value of driving point impedance at the first port and driving point impedance at the second port? Question I will write here. For the given circuit, so what is the value of driving point impedance? Anyone can tell? So driving point impedance for this circuit. This is a two port network. So anyone can give the value of driving point impedance for the given. Here I am taking the 2-port network. So since it is the 2-port network, so definitely we have the 2 driving point impedances. One is at the port 1, another is at the port 2. So what are those driving impedances? What is the value of the driving impedances? So anyhow, I want to tell one thing. We have Z parameter. We have the 4 Z parameters: Z11, Z12, Z12, Z21, and Z22. Right? So among these 4, which are the driving point impedances? మీకు ఇక్కడ 4 పారామీటర్స్ ఉన్నాయి కదమ్మా, 2-port నెట్వర్క్ కాబట్టి 4 పారామీటర్స్ ఉంటాయి కదా. ఈ 4 పారామీటర్స్ లో which parameters will represent the driving point impedance of the given of a 2-port network? of a two-port network?
Z11,
Z11 and Z22.
Good, good. There is a Z11 and Z22 because Z11 equal to V1 by I1, Z22 equal to V2 by I2. So based on the definition of the driving point impedance or transform impedance, it is defined as the ratio between voltage and current at the same port. So V1 by I1, V2 by I2. So Z11 and Z2 are called as a transform impedance or driving point impedance. Now, what is the value of Z11? Now tell me. Now I am asking, find the driving point impedance function. I am asking driving point impedance. Otherwise, driving point impedance నాకు కావాలి. So మీరు అంటున్నట్టే Z11 is one driving point impedance, Z22 is another driving point impedance. So what is the Z11 and what is the Z22? What is the Z11 and what is the Z22? What is the value of Z11 and what is the value of Z22?
4 plus 1 by S Z11.
4 plus
1 by S.
good, good, right. Fantastic. 4 plus 1 by yes. Good. Next one, Z22.
4 plus S.
4 plus S. That's it. Right. Good. That's it. Because see, generally, if you observe this given two-port network, I told that it's a ratio between transformed voltage and transformed current. That is, transformed voltage means V of S by Z I of S. So that means we have to convert all the parameters into the S domain. We have to convert all the parameters into the S domain. So it is a 1 by S, it is the S, and this is a 4. So it is a 4 plus 1 by S, and this is a 4 plus S. That's it. Z11, Z2. Fantastic. That's it. Right? So that's how, just only I am giving this example to clarify, to create awareness among the what mean by the driving point impedance, what is the driving point impedance, to give that driving point impedance ante ento meeku clarity kosam I am telling this small example. Already we discussed all things, but to clarify, to clearly tell what is the driving point impedance, so I am telling this, I am taking this example. Next. Good. So that's over. That is a transform impedance already we discussed, right? Now, so the transfer function. Now we are going to discuss about the transfer function. See, network functions are transformer functions and transfer function. Transfer function is transform impedance function and transform impedance function, and the transfer functions. Transform and transfer. Okay. So now we are going to discuss about the transfer functions. So transfer function relates the transform of one quantity at one port to the transform of the another quantity at another port. In the previous case, at the same port we are considered. Okay, but here we are considered the one. We are trying to correlate one port with another port. We are trying to correlate one port with another port. That means we may try to correlate voltage at the first port with the voltage at the second port, or we may correlate with the voltage at the first port with the current at the second port, or if it is a two-port network, or current at the first port with the voltage at the second port, or current at the first port with the current at the second port. So how many, if it is a two-port network, how many possible combinations we have? So we have the 4 possible combinations, right? See, the V2 of S and I2 of S. V2 of S and I2 of S are the transform voltage and current in the second port. V1 of S and I1 of S are the transform voltage and current at the first port. So we are trying to correlate the quantity at the one port with the quantity of the other port. If we correlate V1 and V2, then it is called as the G21 of S. So G21 of S nothing but V2 of S by V1 of S. G21 of S equal to V2 of S by V1 of S. That means the ratio between transform voltage at the second port to the and transform voltage at the first port is also called as a voltage gain. It is also called as a voltage gain. It's called as a voltage transfer function. It's called as a voltage gain, voltage transfer function. Similarly, if you try to correlate I2, current at the second port with the voltage at the first port, then it is called I2 of S divided by V1 of S. That is called Y21 of S. It is called as a admittance transfer function. I by V, admittance transfer function. Similarly, Z21 of S, that is the V2 of S divided by I1 of S. That means we are trying to correlate voltage at the second port with the current at the first port. We are trying to correlate voltage at the second port with the current at the first port. That is the Z22 of Z21 of S is called an impedance transfer function. So Z21 of S equal to V2 of S divided by I1 of S. V2 of S divided by I1 of S. Right? Similarly, it is I2 of S divided by I1 of S. I2 of S divided by I1 of S. So that's equal to alpha 21 of S. This is called as the current gain or a current transfer function. Right? So transfer function means it's trying to, that function trying to correlate parameter at the one port to the transformer parameter, transform quantity, voltage quantity or current quantity. It's the transfer quantity of the another port, not at the same ports. If you are trying to correlate voltage at the first port with the voltage at the second port, or voltage at the first port with the current at the second port. Similarly, current at the first port with the voltage at the second port, or current at the first port with the current at the second port. That means one quantity trying to correlate with the another quantity in the another port, not at the same port. Whereas in case of the transform impedance, whether in case of the transform admittance, we are trying to correlate with the quantities within the same port. The V1 of S by I1 of S, or I1 of S by V1 of S at the same port. Right? But here not like that. We are trying to correlate with the different ports. First port to second port, and second port to first port. Right? So this is called the transfer function. Right? So these are some, we will go with some small discussions. So transform impedance, and that means I am trying to transform the circuit in the time domain into the S domain. Generally, we have the circuit in the time domain. I want to transform that circuit into the S domain. For simple explanation, I am taking the resistance. So here, input voltage is V of t, and current is I of t, and resistance is R. If you apply simply KVL, then V of t equal to R into I of t, and apply Laplace transform. Then it is V of S equal to I of S into R, and Z of S equal to transform impedance. What is the definition of transform impedance? So transform impedance is nothing but the ratio between transform voltage and transform current at the same port. That's why V of S by I of S, voltage at the driving point and current at the driving point in S domain transform. So V of S by I of S, that is called the transform impedance, that's equal to V of S by R of S, that's equal to R. Now it is the S domain now. See, circuit in the S domain. So V of t will become V of S, I of t becomes I of S, and it is an impedance Z of S that's equal to R. Transform impedance Z of S that's equal to R. So if you observe here, V of S equal to R into I of S. V of S equal to R into I of S. That's how the simple example how we transform one circuit into the another circuit. Sorry, transform circuit from the one plane to the another plane, one domain to the another domain. It is either from the time domain to the transform from the time domain to the S domain. I'm transform the impedance and the circuit from one domain to the another domain. The circuit containing the only resistance. Circuit containing only resistance. Now we will move to the impedance. We will move to the impedance. Sorry, inductance. Inductor. Right. So now again, I have a time domain electric circuit which consists of single inductor having inductance value L. Input driving point voltage is V of t and driving point current is I of t. Voltage is V of t and driving point current is I of t. Right? So, if you apply, we know that the relation between voltage across the inductor and current from the conductor inductor, that's equal to VL of t equal to L into DL of t by dt. VL of t equal to L into DIL of t by dt. Now apply Laplace transform, then we have VL of S equal to L into S into L of S minus initial current. IL of 0 minus. IL of 0 minus means it is the initial current. That means initial current flowing to the inductor. So just move this right hand side of the equation toward the left hand side. Then we have VL of S minus L into S into IL of S. Again here a small correction, because this minus will become plus here.